Welcome back. We were discussing in the last class about sintering mechanisms and also the governing equations for mass transfer mechanisms and the role of different sintering variables, and then we also have discussed about the densification, pressure assisted densification, and during compact preparation and the pressurization stage and the thermally activated densification stage. How we can basically control the strain rates and also the pore closure rate. So then we have started discussing about the these things in case of occasions where we are applying the pressure and temperature together. So, we will also start today from there on in this class. So, then like we have discussed in the last class. So, this is basically the resulting expression for this strain rate, that is a so this is theta dot is equal to k theta by 1 minus theta to the power n into a p to the power n. So, in this case the powder aggregate is kept under isostatic pressure and temperature. So, by measuring individual displacements at various points in the aggregate and by imposing the necessary boundary conditions, we can calculate the strain rate like this. So, the corresponding effective pressure P effective is same as derived from the earlier discussed expression, that is degree theta is equal to strain in x, y and z direction into 1 minus theta. So, the pore closure rate can be expressed as theta dot is equal to 3 a second bracket 3 by 2 p theta ln theta by 1 minus theta to the power n into 1 minus theta. So, so this is basically the expressions for strain rate and pore closure rate in case of simultaneous pressure and temperature assisted sintering. The example of that is HIP, that is hot isostatic pressing. So, with that we are done with the different process condition variables and the micro mechanisms of the sintering densification process, and the mass transfer models also we have discussed. So, now let us discuss about the powder injection molding processes, which is one of the key process for powder metallurgy, where we can get net shape parts and also near net shape parts. So, mostly we deal apply PIM for net shape parts, where we basically you add the powder and the binder ingredients, we do mixing of them in a blending machine, and then we granulate the mixture and so that we can get the pellets, and then we mold those pellets by the injection molding machine. Then after post injection molding, we debound the part to take out the polymeric ingredients out, and then after post debinding we sinter the parts, and also then there are some finish operations in case to case basis are generally being executed, and then that way we get the final product. So, these are basically the key steps, that is powder mixing, granulation, molding, removal and sintering. Here powder injection molding PIM can be broadly classified as two techniques, that is MIM metal injection molding when we are dealing with the metal powder, and CIM, that is ceramic injection molding when we are dealing with the ceramic powders. Okay. So, and also based on the size of the machine and the size of the powder particulates and the dimensional features, we also differentiate PIM as conventional PIM and micro PIM. So, these are basically the variants of the process based on the material aspect, and also the shape, size of the part, and the also the kind of features that we are looking for in the developed part. So, based on that we can classify the PIM processes in two ways that has been discussed over here. So, so after discussing the key steps, the post sintering, the compact can be densified, heat treated or machined for enhanced properties and precision. post sintering. So, secondary operations on PM part. So, machining in general machining is not necessary for porous parts, but it can be done to produce specific shape and size, in which case a very sharp tooling with a slight rake is employed. The machine surface is then treated to remove the cutting fluids. The EDM electric discharge machining and laser cutting are also performed to obtain specific shape and size. And then joining. So, joining of porous parts can be done with one another or with solid part, mainly in the case of stainless steel porous components. TIG, tungsten inert gas welding, and laser and or electron beam welding are recommended for satisfactory joining of the porous parts or joining between the solid and the porous parts. So, soldering, brazing are not used. Epoxy resins are also used for bonding of porous parts. And then insert molding, sinter bonding, press fitting are other secondary operations. Powder should be evaluated for their suitability for further processing. Flow rate measures the ease with which powder can be fed and distributed into a die. Apparent density is the measure of a powder's ability to fill available space without external pressure, and compressibility is the effectiveness of applied pressure. So, these are the different important keywords for the powder processing, and also the secondary operations that we generally do in case of PM processed objects. So, when it is the goal is to get near net shape parts, or when the goal is to get the parts which are otherwise from the difficult to process materials, which are difficult to process in other manufacturing techniques. So, but in case of the basic essence of the powder injection molding technique, where the goal is mostly to get the net shape part. So, in that case we do not deal with any post operations such as machining or joining. Okay. So, the evaluation of the particles, powder particles for their suitability for further processing should be carried out by particle size measurement, which can be done the most basic and conventional technique of determining the powder particle size or segregating the powder particles as per their size, so that it can be employed for the application suitable for that particular powder particle size can be depicted as sieving technique. So, where in case of sieving we generally use mesh of different sizes, which ranges from 40 to 9500 microns. So, standard sized sieves are available to cover a wide range of sizes. So, these sieves are designed to sit in a stack, so that the material. So, it is basically a very basic concept. So, assume a cylindrical stack of the sieves. So, like this is sieve 1, and then this is at the base of it there is sieve 2. For example, there are multiple sieves are created, and where the powder particles size ranges vary based on the mesh size. So, which is becoming finer and finer as the powder particles are dropping to the next sieve at the bottom. So, thereby it can be that bigger particles can be trapped at the top and the smaller particles can pass through. So, in that way we can also get an estimate of the powder particle size, and also we can do the gravity driven separation by using different sieves of the powder particulates having different particle sizes. Okay. So, the screens, square screens of different mesh sizes is the most common method to determine the powder particle size. So, in absence of friction, change in density rho during unconfined forging is given by minus d rho by rho is equal to d epsilon r plus d epsilon theta plus d epsilon z. So, here epsilon r, epsilon theta and epsilon z are the circumferential and axial strain increments. So, the strains are interrelated as d epsilon r, that is the radial strain, is equal to d epsilon theta is equal to nu d epsilon z. Okay. So, so radial, circumferential and the axial strain. So, here the radial strain, the increment in radial strain d epsilon r is equal to the increment in the circumferential strain is equal to nu multiplied by the change in the axial strain. So, this is how we can define. So, nu, where nu is the Poisson's ratio. So, incorporating Poisson's ratio, the densification equation becomes minus d rho relative by d rho relative into 1 minus rho relative to the power 0.92 is equal to d epsilon z, where rho relative is the relative density. So, in case of closed die forging, the densification expression simplifies as d rho by rho is equal to d epsilon z. So, in this case only the axial strain, change in axial strain happens, and in other two direction because of the constraint associated with the closed die forging, where the part which is undergoing, the powder aggregate, powder compact does not allow to be strained in the radial or circumferential direction, except it is allowed to get strained only in the axial direction. So, that is why the expression 1 reduces to expression 2 in case of closed die forging. So, for stable extrusion pressure, when we are talking about powder extrusion, so then PR is equal to A K ln R, where R is the extrusion ratio, A and K are the material constants. So, considering local temperature increase, PR is equal to A K 1 minus C delta T ln R. So, where C is equal to dk dt, that is the slope of the deformation resistance against temperature curves. Okay. So, here the schematically the powder extrusion process is shown. So, powder extrusion, powder rolling, these are like the special grade of powder metallurgy processes, where so the powder is canned, evacuated and sealed for the extrusion billet, and then in the step B with loosely packed powder on extrusion, the can may be folded, and C is the penetrator technique used to avoid folding of the can. So, these are like individual techniques that we can go ahead with in the powder extrusion process. So, it can be either canned in a suitable container, and then the ram can apply the extruding load, and that way it will show bulges because of the bulges happening in the can, and in the case where we are applying the pressure directly on the powder aggregate. So, in that case there is no chances of can folding or bulging, and there we can get the desired preform directly from the powder aggregate with the desired dimensional attributes. So, then moving into powder rolling. So, this is a typical schematic which is showing the case of vertical rolling and also horizontal powder rolling and even angled powder rolling. So, with a 2 high roller and with a 4 high roller. So, these are the example of vertical rolling, and then C is the horizontal powder rolling, where the powder aggregate is fed horizontally to the 2 high rollers, and D is the example of inclined angle powder feed into the 2 high rollers, and the associated roll strips are obtained, and then loose powder is fed into the gap of a rolling mill in case of powder rolling to form a green sheet which is continuously sintered and rolled to fabricate a full density strip product. So, you can draw analogy of this powder rolling process with the continuous casting technique that we have discussed during the casting module when we were discussing the casting module. So, that time we have discussed about the similar process. So, in that case it was the liquid to solid transformation of the liquid melt and analogous thickness reduction by the mechanical loading, that means by a rolling. So, in this case here the powder aggregate is getting deformed and in the form of a green sheet, and then it is undergoing sintering and subsequent hot rolling. So that it can achieve densification by sintering when passing through the sintering zone of the sintering furnace, and then subsequent deformation, plastic deformation undergoing hot rolling, and thereby we can directly get the full density strip product from the powder aggregate kept at the hopper. So, this is how we can get. So, there are some other special PM techniques like spray forming. So, here in this schematic you can see the cross sectional view of a plasma spray gun where powder is injected into the arc plume to form molten droplets for atomization or deposition. So, this is a typical example of plasma spray gun, where we can get a coating layer directly from the powder particles, deposition of powder particles over the substrate body. And the second case is the spray forming process, where you can see it uses a gas atomizer to generate a spray of particles deposited on a moving substrate to form a rapidly solidified nearly full density structure. So then, and this is a typical example of the structure development in a plasma spray deposit, involves splats, solidified particles trapped in the deposit, pores and semi-solid particles. So, it is a highly complicated microstructure, because we are talking here about plasma spray deposit, and we are talking about the plasma forming. So, so you can see direct correlation from here. So, this is basically the resultant microstructure. So, it is a highly dynamic process, and because of this plasma spray deposit, so some of the powder particles, they experience complete melting while getting deposited. Some of the powder particles remains in the semi-solid state, and some of them even remains as the solid, or say partial experience semi molten or minimum or negligible melting. So, that is why you can see the the deposition of the coating layer over the substrate. It includes several different microstructure at different region, because of the presence of the semi solid region, splat, molten droplet, pore, etc. So, hence so this plot shows a strength versus diameter plot, or diameter versus strength plot for different processes of the different preparation techniques of the same material. So, a strength comparison of conventional tool steel and powder metallurgy tool steel ingots. So, the PM material has greater uniformity as evidenced by the higher properties, less orientation dependence and lower degradation with increasing ingot diameter. So, as you have seen, as we keep increasing the ingot diameter, you can see that there is a decrease in the strength attributes, that is common in case of both wrought form and PM processed form. However, you can see there is a large gap of properties, variation of properties in case of longitudinal and transverse direction properties of the wrought form of the same material, whereas in case of powder metallurgy processed material, the gap between the properties in the longitudinal and transverse direction is very narrow, and which is also increases with the increasing diameter of the ingot. That means, with the as big the sample is, the gap reduces, and also we can see that it is we can achieve even improved higher properties in case of PM processed part. At least the example can be hot isostatic pressing, where the porosity content is very close to the theoretical density of the material. So, there we can achieve properties which are even higher than the wrought form of the same material, because there are chances of defect formation that generally happens during casting. If you remember, we have discussed about the blowholes, porosity, gas porosity, and cracks, oxide entrapment. So, those defects are inherently nullified in case of powder metallurgy routes, because we can control the morphology of the sintered part by controlling the morphology of the powder particle itself, and that is why also we can control the orientation to a greater extent, because we are talking, if we can control, if you know the orientation of the powder particle also, the microstructure of the powder particle, if it consists of fine grain morphology, then we end up getting fine grain morphology with a significantly higher mechanical properties in the sintered part. So, that is why we can achieve even so in occasions we can achieve higher mechanical properties than the wrought form of the same material. Okay. So, then we will continue. So, now we have briefed about some special powder metallurgy processes. So, out of that, as I told you earlier, that injection molding is a process where we can develop near net shape parts with great precision, and also net shape parts without any need of post finishing, such as machining or polishing processes, any need of that. So, then injection molding process. So, it is a very high versatile technique for mass production of critical macro as well as micro components. So, we can directly achieve raw the final part from the raw material. So, it needs very little finishing, it offers a high automatability, high productivity and lower piece costs for larger volume. So, these are the benefits associated, and then injection molding process. So, you can see this is a schematic depiction of the process. So, this is about the stage 1. So, where you can see that we are basically the material, I mean it can be like I have explained to you earlier. If we are talking about metal powder polymer mixture, then we call it as MIM. We are talking about ceramic powder and polymer mixture, then we call it as CIM. So, whatever may be the powder, I mean polymer mixture, if we are talking about MIM or CIM, is fed into this hopper. So, that is the first stage, that is the powder loading into the hopper and then followed by injection into the die cavity. So, this is the die cavity. So, there where it is getting injected and then holding pressure and plastification. So, this is the stage when you can see that both the die hubs are engaged, both the male and the female hubs are engaged, and basically after injecting the melt, I mean the feedstock or the I mean powder polymer aggregate into the die cavity, the holding or pressurization stage prevails. So, screw rotates for plastification and then that is the stage 3, that is the ejection. So, this is the stage. During this stage, the part after experiencing solidification within the die cavity, it is basically gets ejected from the die cavity, and then we, I mean in case of when we are talking about polymer, then this is the final part that we get from this stage, and in case of metal or ceramic injection molding, this is only the green compact, which then need to be further processed via debinding and I mean sintering route to achieve the fully dense part for in service applicability. So, I mean so this is how we basically implement the I mean injection molding process. So, after raw material feeding, then plastification, then mold clamping, injection preparation, and then injection, actual injection, and this is a cyclic process. So, the sequence, this sequence that we have discussed is repeated continuously in cycles to produce molded parts. So, depending on the material to be processed, one frequently talks about injection molds for thermoplastics, thermoset molds, elastomer or rubber molds, and structural foam molds. So, the functions of the injection mold. So, the basic tasks of a mold are accommodation and distribution of the melt. I mean it can be polymer melt or it can also be polymer metal or polymer ceramic mixture, and then shaping and cooling of the material or additive activating heat or adding activating heat for thermosets and elastomers, solidification of the melt and ejection of the I mean molding. So, I mean all these tasks of a mold can be accomplished with the following functional systems, that is sprue and runner system, cavity, that is venting, heat exchange system. So, so here the several functional parts of the mold is shown, like cavity, mounting and transmission of forces, and then this is the heat exchange system, then ejection system and transmission of movements, then leading and alignment, and sprue and runner base system. So, these are all the essential components of the I mean injection molds. Okay. So, then next, so I mean so the maximum number of cavities. So, at first the maximum theoretical number of cavities need to be calculated for appropriate design of the dies for the injection molding processes. So, then so that is termed here as N1. So, N1 is nothing but the maximum short size SV in semi cube divided by the volume of the part and runner MV in semi cube. So, then if so here I mean so the number of cavities are possible, say assume the maximum short size SB. So, this is the total short size. So, then that I mean so how much part of it is accommodated for individual cavities. So, thereby from there we can calculate the number of cavities that can be kept in a multi cavity mold. So, for example, if I draw a I mean a multi cavity mold. So, you can see so this is a typical example of a multi cavity mold that we can so with a balanced runner design. So, where you can keep one part here, we can keep another part here, and we likewise I mean so yeah. So, this is a typical example. The another example can be I mean when it is kept further apart. So, like when like this. Okay. So, these are the part which is mounted, and similarly this is the sprue, then this is getting separated, and this is the part mounted. So, this is a typical example of balanced runner design that we can generally follow in case of powder injection molding, be it polymer or metal or ceramic. So, you can see, so these are actually 1, 2, 3, 4, these are like individual cavities. So, if we can get the runner and the cavity volume for individual one component cavity, and we divide by the maximum shot size what the machine can inject, we can calculate how many cavities, how many components we can manufacture from one injection shot. So, the number of cavities for thin walled parts can furthermore be determined by the plasticating rate of the machine. So, which is defined here as N2, which is equal to plasticating rate R in semi cube per minute divided by the number of shots Z per minute into part plus runner volume in semi cube. So, it is a more realistic estimation for the design of the injection mold based on this criteria. So, because here it also considers the plasticating rate of the equipment, because even after the maximum shot size is there, so the plasticating rate determines that at what could be the processing cycle that can be implemented in that particular injection molding setup. So, considering that, if we calculate, if you design for the injection mold die cavity, then you can significantly enhance the production capacity, and the number of parts can be developed. So, modern reciprocating screw injection molding machines have such a high plasticating rate that the number of cavities N2 should only be checked for thin walled parts with large shot size. So, an empirical rule state, so N2 greater than equal to 0.4 N1 and less than equal to 0.8 N1. So, so this is the so machine such that the number of cavities N2 should only be checked for thin walled parts with large shot size. So, so this is only need to be checked, this N2 parameter, and where it is ranging compared to the N1, the maximum possible, and this is what actually possible in practice in realistic manner. So, where it is standing, that need to be checked in case of thin walled parts only, and not needed for thick walled parts to be checked. And then thereafter we are moving into the clamping force, again another important design criteria for the injection molding process. So, the minimum clamping force is derived from the reactive force of the cavity, which results from the projected area of all cavities and runners and the maximum cavity pressure. So, clamping force F is equal to AP over here. So, area into the the injection force. So, then the reactive force F depends on the projected area A and cavity pressure P 20 to 100 MPa. So, faulty operations can increase pressure to full injection capacity. Calculation should use maximum pressure and area to ensure mold safety. So, then F max is equal to A max into P injection, which should be less than the F clamp. So, please beg your pardon, so you please correct it. So, it should be C. So, then so then it should be the injection pressure based and the area product should, that means F max that is applied should be less than the F clamp, that means the maximum so the maximum clamping pressure available with the equipment. So, this need to be very much critically followed for the success of the injection molding process to avoid defect formation and also improper filling of the component cavity. The flow length to wall thickness ratio L by H square is governed by the Hagen-Poiseuille's law and depends on the injection pressure P injection. So, melt viscosity and melt flow velocity. So, this ratio is crucial for maintaining proper mold filling and ensuring uniform product quality. So, the flow length by wall thickness ratio derived from Hagen-Poiseuille's law is in accordance with the similarity principle, which can be depicted as here. So, L by H square length to wall thickness ratio is equal to delta P by 32 phi Vf eta effective. So, eta effective is the melt viscosity. So, this is how we can achieve. So, then injection molding, full flow length. So, represents the length of flow through the mold cavity and hydraulic radius h defined as h is equal to 2 into W into T by W plus T, where W is the width of the cavity and T is the thickness of the cavity, so hydraulic radius accounts for the effective cross sectional flow area. So, this is the hydraulic radius we can determine likewise. Based on the width and thickness of the cavity, and the parameter phi is equal to 1.5 for cases where width is much larger than thickness. So, this is typical in injection molding scenarios. Then velocity of flow front Vf, recommended value for calculations is approximately 30 semi per second, which ensures efficient flow dynamics, and maximum injection pressure. So, common injection machines can achieve pressures or can go up to 120 megapascal. So, apparent effective viscosity. So, this viscosity of the melt depends on the material type. So, these are basically the important characteristics for getting design, mold design, and also for the process design of the injection molding process itself. So, to achieve the much needed success in the process, to develop the defect free parts. So, these are what being discussed. So, apparent effective viscosity. So, for amorphous materials, eta exact is equal to 250 to 270 Pascal second, accuracy in the range of plus minus 10%. And melt temperature Tm is equal to Te plus 150 degree centigrade, and where T is the freeze temperature. So, it is these are the parameters needed for amorphous materials, and for crystalline materials eta exact 170 Pascal second, accuracy melt temperature Tm should be Te, that is freeze temperature, plus 250 to 375 degree centigrade. So, these are basically the empirical outcomes that has been rigorously tested and evaluated, and that is why it is documented for your knowledge. And here for amorphous metals, the length flow length, which is shown over here earlier also. So, flow length can be determined as from this empirical formula, and for crystalline materials the flow length can be determined by this crystalline formula. Okay. So, with this we will go into the critical summary of runner systems in case of injection molding. So, runner systems, so the runner can be of two types, that is one hot runner and the cold runner. So, these are the two different kind of runner generally being used for injection molding. So, what is the difference in these two runner systems? So, in case of hot runner systems, the material which is entering into the mold cavity, it is always remains in the fluid state in case of hot runner. So, that is why it never freezes with the material, the polymer or the feedstock material, that is metal feedstock, that means metal polymer mixture or ceramic polymer mixture, it never freezes in the in case of hot runner. It only freezes for the component, and then the component gets easily detached from the runner. So, so one way the advantage is, it is the post processing time, and also the marks generally have presence in case of cold runner system of the runner system, and gate marks, they are some present in the component, the green compact after ejecting out of the mold cavity of the injection molding machine. That is not the case in case of hot runner system, it gets ejected easily, and also in that way the material wastage is much lesser, because the analogous geometry, the gating geometry that is needed to fill the component, they are never getting frozen. So, this is the case of hot runner system, and in case of cold runner system, it is the runner and gating arrangement. So, they are also getting solidified with the part itself, and they need to be removed, trimmed off from the part to get the desired part geometry. So, the key components of a runner system. So, sprue bushing receives molten material from the injection nozzle and feeds into the runner system, and then runners distribute molten plastic to mold cavities, especially in multi cavity molds, and gets narrow cross sectional areas that ensure easy and clean separation of molded parts from the runner system, aid in fully automated operations, optimize melt transfer to cavities at desired locations. So, the types of runner systems. So, standard runner systems are machined directly into mold plates at the parting line, melt remaining in the runner freezes and is removed with each shot. So, this is a typical case of cold runner system. We will discuss about that in detail later. Advantages: recyclable frozen material for thermoplastics. So, in case of thermoplastic polymers, it can be recycled. However, in case of thermosetting polymers, once molded, the material become irrecoverable, leading to waste formation. Okay. So, with this we are stopping for this class, and we will continue with the powder metallurgy, the leftover part in the next class. So, thank you till then, goodbye.